Okay, good morning, everybody. Welcome to seminar. I am having the privilege and pleasure of introducing our speaker today, who is Proto-Dr. Evan Nuñez from CalTech Astronomy Astrophysics Department. But Evan is someone that I've known for many years now. I met him first at an American Astronomical Society National Conference in winter of years gone by. I forget exactly which one. It was many years ago. He was at that point a student at El Camino Community College, which has historically been one of our great feeder schools. Sends us some very good students as transfers. He had completed a summer research internship at the University of Wyoming as part of the COMPARE program. It's called Calbridge Summer now. And he was trying to decide which four-year university to transfer to. He had offers in hand from some pretty big names like, correct me if I'm wrong, UCLA, San Diego, Santa Cruz, Berkeley was in there. And he chose to come here. He can probably tell you why. But when he came here, he became a Calbridge scholar for 2 years, and he was so eager and enthusiastic to start doing research that I think, did I hire you even before you started?
Yes.
Yeah, so I hired him to work on one of my grants in my research group for the summer before he began his junior year. And then the following summer, he did an RU program at the Smithsonian Astrophysical Observatory at Harvard, which is another fantastic program. We've had some other students go to that one before and since. And then he applied to grad school and ended up getting into the most competitive graduate program I know of in SoCal, which is CalTech. And that's where he's been since. He went there with an NSF graduate research fellowship, which is quite competitive and gives 3 years of independent funding throughout the graduate school. While he was there, he actually published a paper based on work that he did with me. He's the lead author on that paper, based on work he did as an undergraduate. And I understand today he's going to be talking about the work that he's been doing for his PhD that he's in the process of finishing this year. So Evan, it's great to have you here. We'd love to see you. We've been proud of you. I know I speak to all the other faculty that we're very proud of all you've accomplished, and we can't wait to hear more about it.
Thank you for the amazing introduction, Matt. It is so very nice to be here. It means quite a bit. I mean, it's like a full circle moment from a lot of respects. I am indeed in the Halloween spirit. I'm dressed as a very lazy Bob Ross. So I'm not going to button down the shirt because, you know, not my style. But yeah, I am indeed in the spirit. So I'm going to sort of break down, I think, more relevant things for just about every person in the audience. So things that are going to be split between undergrads, everyone, and then of course faculty for future prospects and what have you. And I'm very indebted to some amazing people that I'm going to be highlighting throughout the talk, and I'll try and verbally mention some things. And everybody whose name you see explicitly here has been instrumental in my PhD. So the big picture of my research is I'm trying to look inside and out, and this idea of galactic, or this idea of introspection is going to be littered all throughout the talk. I think it's been a very valuable tool and a pretty important aspect, I think, of where I currently am now. It's been a very long journey, but I'm working specifically with Chuck Slidell, who's at CalTech, and my other advisor who has the same name as me, Evan Kirby, who's at Notre Dame now, which has been kind of interesting having two different home campuses. Worked out all right, for what it's worth. One of the things that I always like to start off my talks with is, there we go, is just as a reminder for those of us in academia who choose or hope we do stay in academia that we're very fortunate to do what we do. So I'm showing here a Cal Black Pomona alumni, as well as a person in astronomy who was we lost, who really changed my perspective on this when it comes to the type of work that we're trying to do. I argue that astronomy is a science of intellectual curiosity, connectedness, and humility, not necessarily practicality and competition. There are, of course, competitive aspects of every field in terms of getting grants and what have you, but the core and root of it all should be collaboration. I think, especially in astronomy, given the different land issues that have been occurring that have been shrouding that we have to acknowledge first of our wrongdoings and then try and do our best to change them as we go forward. And I think for all of us who are doing just fundamental research in general, we need to learn, share, be kind, and uplift one another. I don't think that's too much to ask for. So my talk is going to be broken up into 4 parts: my journey, my research, my future, and my resolve. I thought this is kind of cool and poetic to put it like that, but you know, it should be a good time. So we're going to start off quickly by looking at how I got here. Matt actually did a fantastic summary of it all, so I'm just going to not spend too much time. But everything for me, at least in terms of when it comes to higher education, started off at West High. So I was, let's see, the second half of my childhood was in Torrance, California, where I finished up at West Torrance High School. When I graduated, I had a few offers from universities that I weren't that interested in, and we had a really nice, strong connection with the community college that I went to, El Camino, that hooked me up and linked me up with the MESA program, the Mathematics, Engineering, Science Achievement Program. I would be remiss if I didn't say that, like, that program, I would argue, is a huge pivotal reason as to why I'm here. CalTech, and even for what it's worth, Pomona got pretty refined versions of me as a result of, you know, really good training that I got when I was at El Camino. So while I was at Elco, I had some really very unique experiences. The first was that I was in JPL for a summer. Actually, it was for like 6 months. It's called the J+, the JPL Undergraduate Scholarship Program, which is geared towards getting community college students really is to make them as competitive as possible for future experiences. In my case, all I really knew was that I had lab access for 6 months, which was great. We had, you know, fun, you know, professional development and stuff like that, but it was a time. Most importantly, that following summer, as Matt mentioned, I was part of the Camp Hair program, which is now called the CalBridge Summer, where I did a very, very fun 10-week stint at the University of Wyoming, which admittedly, I didn't even know that university existed. And when I told my family, they were like, yo, be careful out there. You're probably going to increase the Black population by like a factor of 2. It was kind of not wrong. But I actually had a great time out there. Most importantly, I was able to see science from data acquisition, or specifically astrophysics from data acquisition, like actually going to the telescope and collecting data, to reduction, to processing, and then finally to science. And I found that I loved every part of that process. So it was instrumental in, again, me wanting to continue going forward and where I currently am at the moment. So, as Matt mentioned, I spent 3 years, and I was, of course, ready to transfer that by that point. And so I had some really good offers, and Pomona was actually the best offer that I had, specifically because of the CalBridge program. Really, it was threefold. First was its location allowed me to stay at home if I wanted to. It's a little bit of a drive, admittedly, so I ended up moving out here, but that was a plus that I wanted to take advantage of. The second was Matt actually got in contact with me specifically at one of these conferences. It was either AAS or one of the Pomona seminars, and effectively promised me a research position. I talked to every faculty member at the UC. Nobody was able to give me anything besides, you'll probably work with us. And I was like, no, you will work with me if you come here, if you want to, obviously. And then the final part was CalBridge and the support that was going to be offered through that program, specifically the mentorship as well as the finances. When you have that combination of those three facts, no other school came close. So for me, it was an easy decision. The only hard part actually was the sort of reaction of folks being like, "Oh, you're going to Pomona? Okay, good job. You'll do just fine." Like, as if this was a downgrade compared to some other schools, which is crazy. So while I was at Pomona this summer before I started, I researched with Matt and Bree. You don't see Bree; she's on sabbatical. Where I was like a little bit of the research that I did, but that resulted in my first paper that I actually had to finish in grad school. Whatever, no worries. And then the following summer, I spent the summer at Harvard, specifically the Smithsonian Astrophysical Observatory, RU, which was a fantastic time. It was probably the most productive summer that I had, because at that point I had like 2 or 3 years under my belt. And then I applied to grad school. I thankfully I feel like very lucky from a lot of respects, a lot of good offers. And found myself at CalTech, where I'm being supported by the Graduate Research Fellowship Program. So for those that are applying or thinking of applying to grad school, please feel free to take my contact info down. It'll be on the last slide. What I want to note, though, is that I've effectively seen like every level of prestige, resource, and climate at these universities, and every single place has been unique. I just want to sort of point out that Pomona was a fantastic institution and still continues to be. And I'm saying this now, of course, in hindsight, but I've seen of a lot at this point. Of course, I have a lot more to learn, especially for like the real senior faculty that are like, oh, yeah. But nonetheless, Pomona is a special place. Now, I would be remiss if I didn't mention more explicitly these programs that have helped me, and I really do think that this extra support in combination with my hard work and of course family support that I had is another reason why I'm here, at least still smiling. I'm sure I would have gotten here at some point, but I probably wouldn't have been as happy. So MESA, J+, NCAS, this is the NASA Community College Aerospace Scholarship Program, Campare, and the University of Wyoming REU when I was at ELCO as a community college student, which is very unique, by the way, to get a research experience that early on. And then while I was at Pomona, of course, the CalBridge program, I call it the Pomona Astro REU. I'm not sure if you actually gave it a name or not, but I get one for you.
We had another summer with more students in it that we gave it an official name. That year was mainly you and a couple others around, I guess.
For sure. Cool. So that was the year, that was the name that I gave for it, the best year. And then again, the Smithsonian Astrophysics REU, which was a really good time. So I, of course, can't get away without showing some pictures and some amazing times, just to more explicitly show some of the fun stuff that happened. So back in my day, we still had the Capitol Key building here, but of course it was unfortunately built along a fault line, so needs to be demolished. These pictures actually turned out to be a lot better than I thought. I had no idea what I was looking at or why I was looking at, but turned out okay. But this was probably the most special, or this is the most special one here. Of course, which is why I have it front and center, because my entire family, actually, no, it's a small part of my family, like my real close family, showing up and supporting me for my graduation from Pomona. For those curious, I am the first, let me see, I think I'm the first college degree in the family. At minimum, the first bachelor's degree in science, the first associate's, the first master's, and of course now I will be the first PhD in the family as well. Even though graduation should be kind of taxing, we all celebrate. I'm flying everybody up with my Ph.D. So I was going to spend a little more time on this slide, but I just had a great time, and I really liked it, and I loved it. I also have to acknowledge too, though, that it was tough, man. I spent a lot. This is hilarious, by the way. So for the youth, what you now use is Instagram Reels was once Snapchat Stories, and so this is actually a story from two of my folks that I hung out with a lot. Their name is Aaron, Kim, and Jennifer. And we actually all went to Switzerland together to go visit CERN for a summer. It was one of their open houses. They do it every 4 years or so. But I was tired, man. It took a lot of effort, and so this is just my clear beacon, I guess, to all the undergrads that yes, it is taxing. Even me as the polished version that you're seeing, there's a lot of hard work that went into it. And this actually gets to my unsolicited advice. So this is for the students. Stay disciplined, in my opinion, and at least for me, motivation is very shiny soil. Some days I feel very excited to keep working. Some days I didn't, but being able to sort of average across that by having some offset to whatever that curve is and just sticking with that really matters. You have schedule, stick to it, right? It has to be all internal. Prioritize your health, but also find ways to keep pushing, right? And of course, this is hard to do, right? It's very much easier said than done, but you have to figure out what works for you. Second is to remember that grades are your academic currency. This is one of the most important, I would argue, aspects, it is the most important part of your like to actually learn something while you're doing it. Go to office hours. Even if you have half of what you think may be a good question, just go chop it up with your professors, right? It's literally their job to talk to you during office hours. Go say hello. Their letters and the connection that you'll be able to get with them is going to be very useful for you later on. Also acknowledge or also understand too that research and whatever other extracurriculars that you have going on have to come second. You may hear varying pieces of advice about this, but I never put research above my classes. And mind you, I wanted to. I really did. As a matter of fact, I would use research as a treat for myself whenever I finish. Like I'm like, okay, if I can finish up this problem set, I'll allow myself to research for like an hour or something like that, right? So if you kind of gamify the system to get the efficiency that you want or whatever, then that also works. And finally, summer internships, and really internships in general, are going to be the biggest difference between whether or not you're employed when you graduate. I cannot stress this enough. Whatever field that you want, getting internships in that field is going to be incredibly vitally important, regardless if you're going into industry, specifically engineering, whatever flavor of engineering that you want to, tech, whatever flavor of tech, grad school, of course, whatever the case, get internships and apply to a bunch of them because they are unfortunately very competitive. In my case, I actually got away a little bit lucky. I mean, I feel bad for your guys' cohort now because it's a slaughterhouse out there, dude. I would say a minimum of 10, something like that, for whatever summer. And again, they make a difference though. So I will come back to this as well. Now I want to just quickly highlight my research interests thus far, really interesting stuff that I've worked on. So my first project actually at the University of Wyoming was working on high redshift quasars. That was a fun one. And then I came here and worked with Matt and Bree. We're looking at star formation. Specifically, I was looking at the X-ray emitting stars that were very young. We can use them to try and date and age date some of these stars. And then as I went to Harvard and now at CalTech, I'm a lot more interested in large-scale galaxies structure. It's been a really, really fun time. Each of these has at least led to a poster or something like that. And then the work that I did with Matt, regarding the Korean evidence here, which is a huge team, it's a fantastically large complex that I still haven't seen yet. You have to go to the Southern Hemisphere to actually see it. One of these days, I'll have to make a trip down there. That led to my first paper, and then my subsequent papers have now come to grad school. As a result, again, the big picture is trying to understand galaxies, as many different aspects as possible. So that was the first section of the talk. Hopefully that was somewhat interesting. At the very least, if there's anything that you didn't take, that you take away from the talk, please let it be those slides. Again, just try your best, stay disciplined. So now we're going to talk, now this is going to be more for the entire audience here, is my thesis research. Again, I'm going to try and make the case for galactic introspection. This is actually a fire simulation that I unfortunately had to convert to a PDF. But the point that the slide basically makes is that it needs to show some of the dynamics that one has to account for if you want to truly model galaxy evolution. And the takeaway from this was that galaxy evolution is a messy, complicated process that has many size scales, mass ranges, and epochs that significantly affect the galaxy's properties at any given time. But especially at the epochs that I'm looking at, which is at redshift 2, which is near the peak of cosmological star formation, these galaxies are vigorously forming stars and therefore ejecting lots and lots and lots of gas. The reason this matters at all, also, I'm an observer, so I actually want to see all of these objects. If you were just to look at the largest scales, every galaxy is basically composed of there are three mass zones that affect the evolution of a galaxy. The first is the interstellar medium, which is where we reside and where we have all star formation. You effectively have conditions for dense gas to form. Once stars form, you have massive stars, and then massive stars form in clusters and they explode at some point. Those explosions drive, my bad, I hit the wrong button. There we go. So those explosions drive these galactic outflows that I'm showing, or that are shown here. This is a cool little graphic by Molly Peoples, who's over at Space Telescope Science Institute. Those outflows then make their way out to the circumgalactic medium. This is a reservoir of mass that's surrounding every single galaxy. Once it makes it to the CGM, it really has two choices. Either it makes its way out to the intergalactic medium, where you have a bunch of hydrogen and pristine gas, as we call it, metal-free gas, or it actually falls back onto the interstellar medium. All while that's occurring, you have this pristine gas, we think this habited filaments, that's coming from the intergalactic medium, falling through the CGM, and then onto the ISM. So more explicitly, the CGM is a very, very important mass reservoir, intermediate reservoir, and really a transition between the interstellar medium and the circumgalactic medium. In other words, these three different physical processes: outflows, recycling, and accretion. This is very important because the fact that we see stars forming all throughout cosmic time suggests that the ISM must be refueled with this mass. So if we have mass that's being ejected, it's going to fall back onto it. At some point, we need to account for that. As I mentioned before, at redshift 2, galaxies ubiquitously show strong galactic outflows. So if we truly, again, want to understand and start to put anchors down on galaxy evolution, we have to account for this incredible amount of mass that's being ejected. Now, it turns out that we've learned a pretty decent amount about redshift 2 galaxy, the ISM of redshift 2 galaxies. Folks, specifically in my collaboration, it's called the Keck-Brown Structure Survey, which we'll talk a little more about, has spent the past 30 years or so developing many relations and doing a lot of incredible work. For example, we were able to find that if you were just to take a galaxy of whatever mass that you want to, and look at that galaxy at redshift 0 versus redshift 2, it'll be more highly star forming. It'll have a more dense electron density, or have a higher radiation field, more massive stars, so on and so forth. So that one's okay. It's just yes.
So that question about Z equal to 2, does it fall into the matter-dominated, dark energy dominated? What phase of the universe does it fall to?
Yes, so this would be it would be matter dominated. Yeah, because you're well past the any of the very early reionization always forget, yeah, but yeah, we're in the matter-dominated era.
Matter-dominated.
Yes.
Can you remind me when exactly the dark energy dominated like starts? What's the? I mean, I don't know. That's why I'm
Good
asking.
question.
Like now.
Yeah,
Yeah,
basically,
no, no,
yeah.
but why does it start? What's the
I mean, like now, when we're just going from matter dominated.
Good dark.
right now?
Yeah.
Yeah, okay.
Good question. That's good. I actually hadn't thought about this in a while.
So don't confuse dark energy important with dark energy dominated, I guess.
Yeah.
Like we can measure the impact of it further back, but we would
Yeah,
say
I'm saying
dominated.
dominated. I'm saying
Yeah.
dominated like which is like dominating the mass.
Yeah, if you coming into the future.
Yeah, it is a future.
So, the issue is that the circumgalactic medium, unfortunately, is really hard to detect. Really, it's because it's very diffuse and doesn't emit photons very readily. So, what one has to rely on are these line of sights that have quasars towards the back of them. It turns out actually this method has been very fruitful at redshift 0. There have been lots of studies to basically show that you expect to have more metals and or especially more hot metals around star-forming galaxies, for example. But at redshift 2, this has been really difficult to do. So I want to explain the method a little bit, just because for me it was, I don't necessarily think some of this stuff is intuitive. So if a galaxy is nearby, you actually can detect its circumgalactic medium in this, at least the continuum, via emission maps. And so in particular, this has been done, X-rays, but as well as a few other ground-based telescopes, depending on what line that you're looking at. We can also do this at redshift 2 if you're looking just at hydrogen, specifically alignment alpha. So you're limited to very few lines, basically, if you try and directly image the light. Well, you can also use the galaxy itself as a sort of beacon to sort of light up the gas that's around it. The issue there is that you don't know where the gas lies. It's somewhere between you and the source, right? But in my case, I want to explicitly look at the CGM gas. There are ways that one can disentangle this, but since it's not necessarily trivial to do that, we're also going to put a little meh sign here. But what one could do is use a background object that effectively offers a continuum for the CGM gas to absorb away. And I'll explain what that means a little bit more. And so this is the method that we're gonna rely on to do it. These are unrelated background sources that we're going to use to try and observe and measure the CGM of these galaxies. So what this looks like, this little cartoon figure here, is that we have us looking towards here. We have our galaxy. You can see it's a lot of emission to ISN. And again, surrounding it is this halo of gas. So what we want to get is a spectrum of this background quasar. For those curious, what this actually looks like is the following, where you have your background quasar that's very bright, then you have your foreground galaxy that's very faint and has some projected distance that's nearby. So if we were to get a spectrum of this quasar, we have the following. In the red here is the continuum of that quasar. We have hydrogen emissions coming from it. And if we go to the redshift of the galaxy and look at the wavelengths that we would expect there to be, for example, hydrogen absorption. In this particular case, it's the N=1 to 2 transition for those that are taking quantum 1216 angstroms. Yes.
Because I know we have a lot of non-astro people in the room. I think it might be worth pointing out that quasars are accreting black holes. Then they're shining based on the release of gravitational energy falling into the black hole. So black holes are not black. Let that sink in for a minute. That black hole, accreting, is way further away than the galaxy Evan's interested in. And look how bright it is still compared to the galaxy Evan is interested in. I just think that's nuts. Like black holes turn out to be some of the most luminous objects in the universe, and it's not widely appreciated.
Absolutely. Yep. And so in our case, exactly, actually a lot of these objects literally look like stars, and that's where this name comes from. They're called quasi-stellar radio sources, or quasars, because again, they look just like stars in the optical, until you actually get a spectrum of these objects. In our case, the fine details don't matter because all we need is the spectrum of that background object, because it is so bright. It has continuum that it'll let the gas absorb away. I think I saw a hand over here.
Oh yeah, I was just wondering, what are these like what are the wavelengths?
Yeah, good question. So one wavelength here, I'll actually get to that in just a moment. Yeah, it'll come up. So if we look at the wavelengths where we'd expect there to be, for example, hydrogen, we would see this here, and this is actually a fun example of a absorption system called a damped alignment alpha absorber. And what we would actually see in the quasar spectrum is this. So we can actually see this is looking at the peculiar velocity. So basically the velocity relative to the expansion velocity at that particular redshift, or at the galaxy's distance. And this is what we would see. You can see this very, very strong, it's called damped absorption because of these wings here. those metal lines, and then over here, we have very, very clean metal lines that are in a very nice part of the spectrum. And in particular, this one here is actually a doublet, it's a carbon 4. So that's 1548 angstroms. And we can see once again, we have velocity on the x-axis there, and then we have the metal absorption for this particular ion for the system. So this is the method that I'll be using. And the difficulty with this is that finding these pairs is very difficult to do. And then it's even more difficult to actually detect the galaxies because of how faint they are compared to the background object. So what we have thus far, there's been lots of surveys that have done this work. And we had an emerging picture of the circumgalactic medium based off of these observational results. So first, there appears to be this hot volume-filling phase of hot gas. And then intermixed within that very, very hot gas, you have these very cold, dense clouds, these diffuse but very metal-rich clouds, these sort of neutral ambient clouds. You have mixing that's occurring, inflowing gas, outflowing gas, and what we get from the quasar sideline is a mixture of all of it. And that's really hard to disentangle. But you work with what you got. So what also shows is that this means any given quasar sideline that you're looking at may not necessarily be representative of the entire circumgalactic medium of that particular galaxy. So what we need to do is build a very large sample of these galaxies, and currently I'm shooting for 50. They're at these very small projected distances, so you're looking very close into the galaxy. What we want to do then is try and actually connect those CGM properties to the properties of the galaxy. So for example, what's the mass of the galaxy? How vigorously is it forming stars? What's the metallicity of the galaxy? Because this has never been done at this redshift before. Now, there are lots of open questions as a result of the very low sample size that exists at this redshift. The first is, how does the low mass galaxy circumgalactic medium look compared to a high mass? Do the metals that we expect to see in the circumgalactic medium, do we expect those to vary as a function of, for example, how the galactic outflow strength of the galaxy currently? And it turns out that there always appears to be detections of this unbound gas, a gas that's just completely has a velocity that are above the escape velocity of that particular galaxy. So what is that? What are those particular objects? So I built a survey over my PhD to actually do exactly this. So our survey, I put this in quotes because then I'll explain in a moment, will provide the sample and data that we actually need to do this very painstaking work. So I'm very proud of my acronym, so we're all going to look at this together. This is called KBSS-InCLOSE. So InCLOSE stands for the inner CGM of QSO line of sight emitting galaxies, because we're looking at quasars and are using the line of sights that have quasars in them with galaxies surrounding them. Yes, thank you, Pomona. Yes, yes.
It would have been hard to work that Q into the.
That's fair. You know, all right. I tried it. I think it's perfect. So what we're doing specifically, right, is we're trying to directly connect the CGM and the IC of these galaxies in this very particular redshift range within about 100 kiloparsecs of a quasar. So this is going to be sort of our refrain that we're going to keep coming back to as we build up the sample. But what I want to note and first acknowledge is all the hard work that's gone into this. So again, I'm effectively extending the sample that already exists called the Keck Structure Survey. And I'm very, very thankful and I honestly feel very privileged to be a part of it. It's been literally 30 years worth of work. So the first results and the first paper that I wrote for the sample is concerned with two QSO sidelines. The phone numbers don't matter. All you need to care about is that we have one galaxy towards one of them called G1Z2. It's a galaxy called G1 at a redshift of 2. And then another galaxy towards another quasar sideline, N1Z3, called galaxy N1 at redshift 3. For those curious, actually, this is one of the first galaxies that were discovered using what's called the Lyman break technique, where you can effectively just use the flux in images to put some constraint on the distance of the galaxy. This was 1995. I was -1 years old. I love that joke because my advisors hate it, so I had to use it. It's great. Nonetheless, these are very interesting sidelines, and the fundamental question that we were asking is, given how close in these galaxies are, can we recover them? And if so, what else can we learn from them that hasn't been done thus far? So, the first thing to do is to acquire these far ultraviolet data cubes. And really, these are these redshifts, photons that are in the optical. Photons that have been redshifted into the optical were once in the far ultraviolet. So these data cubes are coming from this instrument called the Keck Cosmic Wave Imager, and the important part here is that for every image, every pixel that you have in that image has a spectrum. So I'm going to show the results. Oh, shoot, sorry. I'm very, very thankful to a few folks. First off, Nick Brzezinski. These are all folks who are in my grad program that helped me ascend this learning curve. Nick Brzezinski, Juyun, and Yu Huang, who've been very instrumental and helpful with this particular work. So what I'm showing here is an example of some of this data. I'm an observer, right? So I like to show as much data as possible. What we're looking at here on the left is one of those quasars. And if I were to tell you that there was a galaxy in that field, you wouldn't believe it, which is the right thing to do because you don't see it. It turns out that removing this very, very bright object while still while not affecting the very faint galaxy light underneath is not a trivial task. I don't have enough time to explain it. But we're able to do it, and here is the results. But just to guide the eye a little bit better, here are the galaxies once again. And the cool part about KCWI is specifically that, or is because is that each of these galaxies now has a spectrum. So in other words, we now have a preliminary distance or redshift to each of these galaxies. It turns out that all these galaxies also have this great contour here that shows extended emission from the CGM, but again, it's just hydrogen. And all the background quasars also have this extended emission. And in my case, all the stuff that's related to the QSO is contamination. I want to get rid of it. And I've always had the thought, like, it would be great if I had a student that just worked on this, right? And it turned out I do. My student Karen, she's a sophomore at CalTech. She's looking at a very particular type of QSO and the extended emission that we can observe using KCWI cubes. Her name will be on the archive at some point in the next year or so. Yes.
The previous slide, can you go? Yeah, so I'm not an astrophysicist and I don't so. But the James Webb Telescope, does it help with this kind of galaxies?
Indeed, and I will talk about that later on in the talk. Yes, absolutely. Very nice costume. All right. So we now have a bunch of galaxy candidates, and we have. Feel free, go ahead, funnel in. It's all good. Go ahead, funnel in. Funnel in. Funnel in. Okay, walk across the front. It's all good. Any speakers? All right. All right, we're good. We're good. Okay, cool. So at this point, we now have our KCWI cubes. They're pretty deep, and we have galaxy candidates. What we wanted to do now is confirm the distance or the redshift of each of these galaxies. So what we wanted to get is what we call an optical spectrum. So this has very typical emission lines that I'll be showing. Now, I'm very thankful to a professor over at Northwestern University. Her name is Allison Strong. She was very helpful with all of this. Again, observer, wanted to show the data. So we have a very nice emission line of oxygen 3. This is going to be most easily identified emission and strong emission lines that exist. This is oxygen that's had 2 of its electrons ripped off. Very, very abundance in the ice in these galaxies. And we can see we have a very nice clear detection, and most importantly, we get a redshift for this galaxy. So in other words, we have confirmed that it's actually at the distance that we think it is. We did the same. I did the same thing for the other object. I did all the observations and the data reduction myself for those curious. And once again, we have a nice clear detection of oxygen 3 here. We were able to confirm that again, this galaxy is indeed at the redshift that we care about. Very good. So we've learned its distance. We have an idea of the extended emission of the galaxy.
What would be the error bar in this? You see, when you specify.
Yeah. So our errors are about 20 kilometers per second. So this would correspond to a redshift of like, I think it'd be the last decimal place would change.
Okay.
And it's like by 3 or 4, basically, of 3 or 4 1,000ths. So pretty big, pretty precise. Yes.
They're attached to the rest frame, I guess.
That's correct. Yeah, this is all shipped into the rest frame. Absolutely. All right. One other example what we get here, by the way, is the oxygen abundance and the nitrogen abundance. So that'll come a little bit later on. So this represents all the new data that we need for the sample. As I mentioned before, KBSS has lots of data. And so we have a bunch of images that we can use to model the stellar populations of these galaxies. In other words, infer stellar mass. I love showing data. So here is what our images look like without removing the quasar, and here's what they look like afterwards. So I adopted a technique that's been used for a very long time. This actually is easy. The stuff with the data cubes is hard, but this was a little bit easier. But nonetheless, what we get from here is a very nice clean stellar mass. And what I get to do now is sort of try and contextualize the galaxies a little bit. So what we're looking at is that same emission line that I talked about before, oxygen 3 over H beta. So this particular ratio gives you an idea, depending on how you think about it, either the density or the ionization field that is that's bathing the gas that you're observing from. And then on the x-axis here, we have stellar mass. All the gray points are galaxies that are nearby. All the green points are galaxies at redshift 2. And then our galaxies that we care about are here and here. First thing to note is that we can see that they are occupying very different areas of this plot in terms of their stellar mass. So in particular, this galaxy here, N1Z3, is sitting in a low mass regime, whereas the other galaxy is sitting in, sort of literally at the middle of the distribution. So that's interesting. We want to keep that in mind as we go forward. Most importantly, neither of them diverge too much from this particular relation. Yes.
My question has to do with like how come some of the green dot galaxies, some of them is like a line and then others are like a cross.
But like why some of them are above or below the scattered?
It's just one versus two visible horizontal or vertical error bars. Some of them.
Yeah,
Oh,
like
like why
one
some of them
side.
are like why the error bars aren't symmetric.
Sure.
Yeah, it just comes down to our measurements. So for some of these galaxies, we have very, very clear and very thin measurements on both of these ratios, both of these lines. Because really, we're looking at a ratio of the emission line. And then the same thing for the stellar masses. Those actually have more of a set. It's probably the rest of it, but that makes sense. It's basically signal to noise. Some of them are more brighter.
Thank you.
Okay. Now, the cool part is that we've sort of built an idea of what these galaxies look like in terms of their emission properties in the interstellar medium. And now we want to actually look at the circumgalactic mediums, right, which is the interesting part of the talk. So I'm very, very thankful and indebted to Wayne Rudy over at Carnegie Observatory's Ryan Cook at Durham in the UK, and then Louis Focus over at Trieste in Italy. So I'm basically showing the same thing before, but now we're looking at the absorption for one of those galaxies, G1Z2. What we notice is that we have, again, very nice clear detection of Lyman alpha. Once again, this is effectively hydrogen. We have a nice detection of nitrogen, very, very complex oxygen, and then silicon. We can do the same thing for the other galaxy here, detection of hydrogen, a limit on nitrogen, clear detection of oxygen, and silicon. What this means really is that we have a nitrogen abundance, a oxygen abundance, and another proxy for oxygen, because unfortunately these two are saturated, which basically means that the measurements get kind of complicated. But because we have this other alpha parameter, we're good basically. What I also want to show is that if you look at this for this little box here, it turns out that this is very, very fast moving gas. It's like 750 kilometers per second, which is about 200 kilometers per second larger than the escape velocity of this particular galaxy. So this is this is direct galactic outflow ejecta, which is incredible. And it turns out that what we're seeing over here on the left appears to be common for galaxies at this redshift, which is kind of interesting. So an interesting aspect of this, right, is to figure out how do other galaxies compare to this at this particular redshift. Okay, so I just want to remark and pause really quick just to look at this slide. I apologize how busy it is, but when I started the project, I didn't appreciate how much work and how much data actually goes into it. It wouldn't stop me from pursuing it, but this is really what it takes to do this work. And this is why it hasn't been done until now. And so what I now have the privilege of being able to show you guys is the main results from this paper, where I get to combine and compare the properties that we learned about the galaxy and emission to what we're seeing in the circumgalactic medium of the galaxy. And in particular, we're going to be looking at the nitrogen to oxygen ratio. I told you it was going to come back as a function of the oxygen abundance. So this is the first time this has been done explicitly at this redshift. I'm very proud to be a part of that. And we have our two galaxies here, and they're connected by these lines here. So all the background points are local star-forming regions. Everything and all the other colored points are other objects that are very likely CGM gas that doesn't have a host galaxy. And what we notice is that the CGM gas here for that first galaxy G1Z2 is sitting in what we call the primary nitrogen plateau. So what this means is that the majority of its metals were liberated from the explosion of very massive stars. One would expect basically if that's the only thing that's contributing metals to this gas that you're looking at, you would expect as a function of as you move across this space that ratio would be fixed. In other words, the CGM gas is young, and that jives pretty well with the picture of metals being injected from the interstellar medium outwards to the circumgalactic medium. And then if we look at the interstellar medium of the galaxy, right, where you have all the actual metal and star formation occurring, it's sitting on what we call the secondary nitrogen plateau, where because of the, well, especially because of stellar evolution and the fact that when intermediate mass stars, like between 3 to 7 solar masses or so, once they reach a particular part of their stellar evolution, they start to eject a bunch of nitrogen out into the gas. And so as you start to move along this plot, there's going to be a point where you start to get more nitrogen relative to your oxygen. So that's exactly what we're seeing. In other words, this seems to be a very, very clear and explicit story of what's happening with this galaxy. That you have metals that were ejected from the interstellar medium out to the CGM. For what it's worth, this isn't too surprising, but we got to actually show it explicitly, which is very nice. Again, as an empiricist, I love this. Things get complicated, of course, now that we're looking at this galaxy. So we only can, unfortunately, look at the x-axis here. But we can see that the oxygen abundance is the same, if not, the CGM is more metal rich than the Ionized. And that does not jive very well with the picture that I just painted. And we actually don't know what's happening there. Pretty sure that the measurements are right for those that are, playing the devil's advocate. But what's possible is that there are satellites that we actually detected in these data cubes that might be injecting metals, and the quasar solid that we're using is intersecting all of those metals that we're seeing. So it might, in other words, it might be artificially increasing the metallicity of the CGM that we're seeing. In other words, we're actually looking at a combination of a few different galaxies that are launching galactic outflows. It's also possible that the galaxy that we're looking at, the main galaxy, is just shooting out very, very metal-rich gas, which I actually thought was infeasible, but apparently it's seen all the time nearby, so it's possible. And the last one is that perhaps the CGM is just spinning up very quickly, and all the metals that one would expect to be ejected onto the ISM, into the CGM that exists all of there, everywhere, is about the circulating such that that it's effectively the same metallicity as the ISM. And it's unlikely, and actually the fact that we see, what was effectively a very clumpy absorption spectrum refutes that claim. So the jury's still out. Most importantly, I hope that this has been interesting in the sense that we really have to put more galaxies on this space. Like, that's the main takeaway. Okay, so now we're going to be at the second to last part of the talk, where I'm sort of looking at the future prospects of the sample. Due to my time constraints, though, I am going to go through this one very quickly. This is preliminary work that I'm currently writing up, and it's effectively the detection of the first dwarf galaxy in the sample that we're looking at, or that I was able to find. Here's what it looks like in our HST images. It actually has a really weird morphology. It looks like it's broken up into 3 different pieces. And if you look at the actual Lyman alpha emission, which is this hydrogen, you can actually see that this is sort of like the very center of this complex is where this emission seems to be originating, which is kind of interesting. Now, of course, Evan, you're the CGM guy. What does the CGM look like, right? This is what we got, which is also very different from what we've seen before. So we have nice clear detection of hydrogen. And as I showed earlier before, we have this ionized carbon, as well as down here is what is usually very hot oxygen. So this is a very different structure in the sense that it's simple compared to what we've seen before, right? Remember all the different complex oxygen profiles that I showed earlier. And also the actual column here that we're seeing, this H1 is very, very small, which is very, very interesting. So it's possible, actually, if you were just to look at the, like the strength of the oxygen to the carbon compared to the hydrogen, it seems like they could be well described by a very hot metal-rich gas. In other words, we might actually be seeing galactic outflows, once again, directly, which is fantastic. I want to give a quick overview of the entire sample. So what we're looking at is the H1 condensity. So effectively, the strength of that hydrogen absorption that I showed earlier, as a function of their distance from their quasar. The main takeaway from this plot is that there used to be 8 objects here. Now there's 54. So great. The survey actually works fantastic. What's also interesting is that, by the way, the galaxies that we looked at are up here, just for those curious, just for context. What's also interesting is how large of a span this is. This is literally 7 orders of magnitude, right, that we're looking in terms of the H1. Very curious. These distances that we're probing are well inside what we would call the statistical bound of the circumgalactic medium, which once again has not been sampled very much at this redshift. And these objects down here are particularly interesting because they don't have a simple explanation. Like, there's nothing very common about them. Some of them are very faint, and some of our data cubes, some of them are very bright. Some of them appear to be massive galaxies. But we have no idea why their CGM absorption looks like it's so weak. Then the other part of this that I want to mention is that the sample is growing, and that most importantly, I have so much that I want to do, basically. There are so many projects, and I would argue there are even many theses with just the current sample that we have. How do all these properties change as a function of stellar mass? What about the morphology? What does the metallicity look like as a function of your azimuthal angle from the galaxy that you're looking at? Do current outflows affect what you see in the CGM and its properties? The ISM metallicity, the ionization, the electron density, all these properties that one can actually surmise with the current data in hand. And so I'm really excited because there are way more projects than I could actually do. And so I'm looking forward to working with students on this. And the final thing that I want to mention is just the benefit of these new telescopes that are coming online. So JWST, I'm actually involved with a few programs. And it's going to be very useful for the future of the survey, specifically because we'll be able to find more of these galaxies. There was a question earlier about this, but yes, we'll be able to find more of the galaxies. We'll be able to make direct emission, or excuse me, spatially resolved emission maps, which will be, actually that's a little later on. Most importantly, we'll be able to detect, at least for my case, what I'm interested in them, is to get direct metallicities of these objects. There's a very, very faint line that one can use to give you a very good proxy on the temperature of the gas, which is a very, very important aspect of trying to determine the metallicity of the galaxy. We have another observatory that's online. It's one of the most productive observatories in the world, actually, called Pomona. And this allows, once I end up getting time at some point, to look at the cold gas that's in the interstellar medium of the galaxy. So in particular, the gas that's actually about to form stars. And again, that'd be interesting to actually connect to the gas that's currently forming stars. Also, be able to look at the dust that you're seeing in the galaxy. We do have a few constraints on that. This is always a hard part of these talks, that I have so much that I could show, but what can you do? And also, the nice thing about these very long wavelengths is that you don't have to worry about some of the physical processes that would make it difficult to infer some the gas properties that give rise to the lines, which is very helpful. And finally, the 30-meter class telescopes, whenever those come online, will hopefully be able to actually look at the CGM in emission. That's like, I would argue, that is the gold standard in the future. As I mentioned before, the sightlines that we're getting through are very, very useful because you get a lot of detailed spectral information. But as I hopefully was able to show, you're getting a hodgepodge of everything. And so being able to compare both in absorption and emission is really going to revolutionize our understanding of the CGM. The resolution of the 30-meter telescopes will actually allow you to, even at Redshift 2, to make spatially resolved emission maps. So how does the oxygen, how does oxygen 3 emission change as a function of your distance? Are there any, star-forming clumps inside these galaxies that are contributing to the majority of the flux, and maybe that's biasing our measurements, so on and so forth. And I argue that 30-meter class telescopes will be able to sort of lock down whether or not there are any other galaxies that are giving rise to this CGM gas that I'm claiming that we're absorbing. The pedantic and devil's advocate astronomer will always tell you, well, actually, there could always be a galaxy that's closer, which, for what it's worth, is a fair criticism. I think once we get 30-meter class telescopes, we'll be able to, pretty definitively say that yes, either there is indeed a galaxy that's actually there that's giving rise to the absorption, or there's nothing there, and my results from KBSS-InCLOSE 1 and 2 were actually right. So I just want to finish up by saying that it takes a lot of work to get to this point. And, this is now an old head track, I suppose, but the quote, I think, still reigns supreme. It's beauty in the struggles, ugliness in the success. And there are a lot of problems that have occurred, just in my life in general, as I've gone through my education thus far. In particular, there was one point where I ended up having such a bad headache that I had to have my sunglasses on, and I'm sitting there doing problem sets, right? I also made sure to go to the CalTech the Bronco Wellness Center, right? This is sort of what I was mentioning earlier, right? About like taking care of yourself, but figuring out a way to make it happen, right? And actually, the sickness that I got from there has literally still plaguing me till this day, right? So again, this very polished version of me that you're seeing, it doesn't happen overnight. Plenty of sleepless nights, plenty of tears, plenty of sadness, plenty of rejections, plenty of all of that. And so my advice is just, again, my unsolicited advice is to just stick it out. So as a summary, my information is up there for the students. Stay disciplined, raise our academic currency, go to office hours. Summer internships are going to make the difference in your employment. So get them if you can. For everyone, I hopefully showed for my thesis work that the survey works, that this is pretty revolutionary stuff, and that I have lots, we have lots to look forward to. There are so many projects that I've already thought of, actually, that I've written about for some of my postdoc guys, and for future faculty position potentially that one can work on. And hopefully I show up in the first results again that we're going to be exploring a very unique parameter space that just has not been done before at this redshift. And finally, as I mentioned before, these great observatories that are coming up are going to be very, very fundamental in the future capabilities of this work. And again, just want to reiterate, there's so much left to do. So thank you very much for your time, and I'll take any questions.
Okay, so there's visa launch for students, it may not be till maybe 1220 or so, maybe 2011. And you said you think that was a low mass galaxy that you detected. Was it based on the strength of the absorption feature of hydrogen? Was that?
Yeah. So it's a little counterintuitive. So yeah, so the argument that I'm making is that oh no way. Whatever. So the argument that I'm making is that we actually don't detect any stellar continuum emission. And also I tried to get Mossbar spectrum, and just for context, this is the galaxy that we were talking about. There we go. Yes. So I don't detect any continuum emission. So it already puts a good limit on, and this is also very deep Q. It's like 5 hours, so you're getting down to something like 5 times 10 to the minus 19. I have not calculated the limiting stellar mass yet, but it's below 10 to the 9.25 already. We also detect any strong line emission from the Mossbar spectrum, which you actually could explain a few different ways. It's possible that we just missed the darn thing, as I mentioned before. You have 3 little emission knots, so it's possible. Oh, I've been trying, so I'm going to keep trying. And then secondly, this particular pattern of metal absorption, where you have low H1 column density and strong carbon-4 and 6, or in particular strong intermediate ions and strong high ions, is pretty ubiquitous in the low redshift dwarf galaxy CGM. So it wouldn't be too shocking if these trends also appear in redshift 2. Or at least, that's like my hand wavy argument for the CGM. The ISM stuff, pretty sure, but for the CGM, this is yes, I'm sorry.
Oh, my question had to do with how did you handle your stress?
Oh, yes, it's a good question. So for me, I try to take breaks in whatever way possible. Go for a walk, and this of course looks different for every person. In my case, whenever I didn't have class, I always make sure to go to the gym. And I'll do something simple like run a mile, and then go do some workouts or whatever to keep up the list. The second thing is that I impose a very strong time restriction on my Fridays. So I found that I was working literally 7 days a week. Some people they can do it. For me, it's not good for me. So Fridays from 7 p.m. to 11:59 p.m. I did not allow myself to work. If it was 12 a.m., sure, but between 7 p.m. 11:59, did not do it. The final part was just going to the family whenever possible. I know for some of us that might be possible for international students and what have you, but or if your family's far away. In my case, that was you going to visit my mom, sort of visit my fiance. She actually would drive out to me. She'd do that. Let hope it's fine. And honestly, going to office hours, so that was stress too. Because I'd be like, yo, man, I don't know what's going on. Like, what do I do? And he was there. And then honestly, every person I've had that's hard. Was very real.
It turns out that there's more than one of us, I might even venture to say, really all of us on the faculty who are quite used to being sounding boards for students who need to vent, and you'll kind of figure out which professors you feel the most comfortable with and kind of who can serve that purpose for you, right? But we're there. I always keep a box of Kleenex in my office, and it's not mainly for me.
Good question.
Like you ever
Oh,
go
sure.
through your break, you just set up a timer?
I guess this is where the discipline comes in. Yes, I had like a calendars that are, the little reminder that came on, and it's like a lot of self-control to like not, there's some exceptions, right? There's a deadline coming up, okay, you gotta do, but like, then I had a very, very strong insinuating circumstance as to why I was breaking it. So in my case, it's really just a timer and just having the willpower and the resolve, just like, all right, I know this is better for me in the future, so let me just stop, basically. But yeah, better, easier said than done.
Thank you.
I saw a hand in the back.
Yes, hello.
I just wanted to ask why you're specifically observing in redshift 2 and 3, and if there's any other research happening at higher redshifts.
Yes, very, very good question. So, so redshift between redshift 2 to 3 is around the peak of cosmological star formation rate density. So we're just a plotted curve of like star formation rate as per cubic per megaparsec cube as a function of redshift. There's it looks like this, right? And there's basically a peak, and that peak is around redshift 2. So it's a very interesting epoch in the universe's history. The second part is So at redshift 0, there's been lots of work done by Jeff's work, Jason Tomlinson. I'm giving you a bunch of info here. But either way, it's redshift 0, it's been done. It's part of what's called the Halo survey. At redshift 1, this has been done in pretty good access. It's called the CUB survey, the Cosmic Ultraviolet Baryon survey. And then at redshift 3, it's been done as well. These are called the MAC survey, the Muse Gas Round Galaxy survey. But we're still critically missing at redshift 2.
But since it is noon, I think if people need to go, they should be allowed to go now. But I understand the pizza lunch may be a little late, so students and faculty, if you have more questions or want to talk more to Evan, I don't think anyone's beating down the door, so we can hang back here for a few minutes. And after which we will bring Evan over to building 3, room 2011 for his hangout with students only. Sound good? Alright, so yeah, if you need to leave now, feel free. If you want to keep asking questions, yes.
I just wanted to ask, when did you know that you wanted to do like CGS? Like was that always your plan?
Yeah, so that's a good question. So
I know it's not, so don't say it was.
Yeah. Let me cook, man. Dang. Over here running the story.
You should have waited.
Yes. So the short answer is, and as Matt was alluding to, I didn't. Yeah. All of this actually started out with my first project. I really liked 2 advisors, and they had very different styles. One was actually very easy to talk to, and the other was not. And I liked the advisors whose science, that overlapped with me. Anyway, they crafted a project that was similar to this. And one of the natural extensions, there was basically a fork in the road. One was to go the galactic chemical evolution route, so how do metals evolve over time in the initial medium of these galaxies. And the other was, what are the actual origins of these objects that I've been using to do this incredible work? And then from there, as we go further down the line, that is what ended up resulting in the GGM stuff. So, I went into grad school very broadly, wanting to work on galaxy evolution, but later on that I actually got kind of interested in sort of fixated on certain things. Good question. Good to see you both. I saw another hand at some point. Yes.
I was wondering, how often did you have to say no to like family events, social events to be able to pursue work like this?
Often. Wait, for Pomona or a PhD?
For like both.
Poly often, nowadays, not as often. The nice thing with once you make it to grad school and once you get past your first 2 years, the amount of recurring, imminent, and important deadlines just completely gets reduced. I mean, it's effectively 1 or 2 per year instead of 4 problems every week, right? So in undergrad, all the time, right? Most of the time I was sleeping on the weekends because I was exhausted. I mean, you can literally see me right in the pictures I showed earlier. And thankfully my family was very understanding. And in my case, I deemed it as important enough, to end up missing those events. It was really important stuff like grandma's birthday. Whatever needs to be done. If I need to send an email to get an extension, I will. Thankfully, I never needed to, but stuff like that. But it's like a party or a function and that. But I'm also not like that much of a party guy anyways, right? So it was easy. When it comes to then for grad school, I've been since there are not as many deadlines, I don't compromise too much. It's very different. It's a very different perspective, right? It's a marathon instead of a sprint. So being able to set aside time for things that you deem important, like I'm working out often nowadays, I'm training for a half marathon. I set aside Wednesday nights and Friday nights, Wednesdays for me and my fiance to just go do whatever we want to. And then Friday nights to still preserve my sanity. As a matter of fact, I moved up my time, so I'll stop at 5 p.m. on Fridays now instead of 7 p.m., right? There's still sacrifice. And I think it's really up to the individual to figure out what's worth sacrificing. And it's not a trivial answer sometimes. Sometimes you have deadline, but it's a very important event. How do you make that decision? I don't know. Good question.
Sylvie?
Yeah, so you talked about grades being currency, and I'm sure you got really good grades to get into the programs, but obviously also you did amazing research. How did you personally find the balance between when was the right time to focus on grades and how much did you, how did you decide how much to allocate for grades and then?
Grades first every time. Grades first every time. Every single time. For what it's worth too, just for complete transparency, I didn't have a perfect GPA, 3.75, which is pretty good. But like, folks that I had in my cohort, 4.1, which I didn't even know existed in college. I was like, you're lying. Like, it said you got 4.0. Yeah, my grad score.
Yeah, I mean, that doesn't exist here, but I guess some schools include A+s or calculate it differently.
Correct, right? So, like, different folks. But what a lot of academic committees are now starting to look into is both a combination of your upper division classes, how well you're doing there, and then of course your research. Really, what grad schools are looking for, two most important parts of your application. Do you at least have a decent enough GPA that you're not going to struggle through the classes and fail out from that? The second, do you have any previous experience to show that you will do good research at this institution? The third, do you have at least 2 or 3 people that can vouch for you from a research perspective that you can do good work? I got very lucky in that sense because my first research experience was at University of Wyoming. So I got letters from that, and I got letters from my advisors at Harvard. So my 3 were fine. Most of the time, folks have 1 or 2 from their advisor, and then like at least 1 or another from like a faculty member that they took the class thing, right? Who can speak to their hard work, but not necessarily to research. So all that to say, research when I could. Most of the time, you're only going to be really productive in the summertime, anyways. And that's even true for your first 2 years in grad school, actually. But yes, yeah, I'll stop random. But yeah, that's the thing. Grades first.
Just real, CalTech, where Evan is insanely competitive because they get a ton of applications. They get hundreds of applications, but they're actually a pretty small program. I mean, how many students were even in your beginning class? I feel like you could count it on one hand.
It was 5 of us.
Yeah. So you're talking about calling 5 successful applicants from a couple hundred. I mean, all grad school is competitive, but this is like basically what I'm saying is what you need to get into CalTech is not what you need to get into just any PhD program in physics or astronomy. It's as hard as it gets.
That's a good point.
And Evan did not need a perfect Cal Poly GPA to get into the place where it is as hard as it gets, right? He needed a very strong one and good research experience.
Absolutely. But one other thing to acknowledge too is that these programs are getting more and more competitive every year. So any way that you can, advantage yourself over your fellow peers, this is also like where it gets competitive, right? Where it's like, but anything that you can do to give yourself that extra little edge is going to be important. And that means working a little bit harder to get the A+ or whatever the case may be. And it can make a difference. I saw a couple.
Yeah, I just want to thank you again for bringing up the importance of, well, thanks for being here. This is a wonderful talk. But just the importance of office hours. In my time here at Cal Poly, I encountered many students who seemed to feel that faculty were doing you a favor by showing up for office hours. And the reality is you paid them for the office hours.
Yep.
So not going to office hours is like going to a restaurant, ordering a meal, and they're not touching it. So they're not doing you a favor. They're there because you paid them to be there. So go.
Absolutely. Talking over here.
Well, maybe we'll wrap it up and let anyone with bigger questions come to the front. And a reminder, students, you know where 32011 is, right? It's the tutoring room. You go out this door to the right down the hall. There will be pizza and Evan there presently. Okay, let's thank our speaker again for the.
Happy to be here. Let's go and speak yourself, right? Yeah, I think that. Oh, yeah, I appreciate it.
Thank you again. That was really a wonderful talk. I appreciate the balance. It's professional and personal. It's so valuable. Matt